baryons and baryon feedback redistribute the matter so that you get a suppression of the matter power spectrum as you go to higher values of K or smaller scales. So great, the hydro simulations give us a prediction for this matter power spectrum suppression. But the problem is, how do we pick a hydro simulation? So there's a large uncertainty on the strength of feedback, the amplitude and the scale extent of this power suppression. And when we're a cosmologist and we just want one of these lines to give us the model, this is a little bit of a difficult situation. So if we want to test cosmology, which we do in our standard DES analysis, we don't want to worry about getting the shape of these baryonic effects wrong. And so we make the tough choice to throw away all of our measurements on scales that we think are impacted by baryon feedback. So here I'm showing 3 of 20 panels in our data vector, and the blue shaded regions are measurements that we toss in DES. So there's a huge cost to this. If we knew how to model feedback perfectly and we could use the full scale extent of our measurements coming from these billion-dollar surveys, we would do about a factor of 2 better in our constraints on S8, just from modeling baryon feedback well. So I used to spend all my time modeling, thinking about calibrating weak lensing data until I made this plot at the end of DES year 3 and decided we needed to work on other things. Now, to show that the problem can be even more dangerous, let's say we try modeling the full scale extent of our data. And so we used, to demonstrate this, I'm using a new model here that modulates the strength of feedback with a single free parameter. And what we find is that the strength of feedback, or the cosmology that we get, is absolutely degenerate with the strength of feedback. And so you can very clearly see that if you underestimate the extent of your feedback, you get a low value of S8. Now, this point wasn't so appreciated until work I did with Georgia Staffiu, where we put forward that you could underestimate the strength of the feedback, and that would explain the S8 tension entirely. So we proposed that this S8 tension wasn't a difference between early universe and late universe. It was a difference between linear scales and nonlinear scales, and put forward a nonlinear solution. And these constraints that I'm showing here are how much you need to adjust the nonlinear scales of our model in order to reconcile the lensing measurements with the CMB measurements. So let's say that we assume that Planck is perfect, and you can guess which one of us in this paper have made that assumption. Let's assume that the CMB is perfect. How much do you need to suppress power on small scales to fit the weak lensing measurements? So that signature is great. A range of dark matter models do this, and we can be very excited. But we must rule out that feedback isn't doing this. We know that AGN feedback gives you this signature, but the signature that you get from AGN feedback is much less extreme than what we're seeing we need. So the question is this new physics, or are we severely underestimating the impact of AGN feedback in our simulations? So at best, the S8 tension is tanking our power from our very large surveys that will run for decades. And at worst, it's biasing our results. With Leah Bigwood, we set out to learn more about feedback and to improve the modeling situation. And we tried a new approach where we wouldn't throw away the data. We would use a very flexible model that's been put forward by Aurel Schneider and Romain Tessier called baryonification. And we would analyze our cosmic shade data with this model. But the problem is that has a huge cost, because it also has a cost because we have 7 free parameters then. So it also tanks our power. And so our approach is to constrain these parameters by jointly analyzing the weak lensing with the KSE effects, which is directly proportional to the electron density and gives us a handle on those gas parameters. Now, our analysis gives us a higher value of S8 with a loss of power in our S8 precision. But the more interesting result was when we turned the question around to say, what does our data tell us about the astrophysics? So we're using here weak lensing and KSE data for the first time to constrain how much power suppression this data wants. How much do we expect? And now we have data to compare to these hydro simulations predictions. Now, we want really extreme feedback in this analysis. It's more extreme than all of the simulations. And so is the data wrong? Is one criticism we got. The other one is, what is this baryonification model? Does it make sense, or is it causing you to go into these non-physical scenarios? So to tackle that criticism, we teamed up with Ian McCarthy and the Flamingo team to measure KSE in the simulations themselves. Now, Flamingo simulations are calibrated, like many other simulations, to X-ray data. So the black data points show the X-ray gas fractions. The Flamingo simulation is shown as the green line. And what we really like about Flamingo is that they gave us these variant simulations where they don't force the simulation to agree with the X-ray data. They let it deviate by 2, 4, and 8 sigma. And that gives us a more extreme power suppression in that simulation. When we measure the KSC, we find that Flamingo cannot describe this data. In fact, our simulation prediction is about 7 sigma away from the KSC measurements. We repeated the process with the Flamingo variance, and the only model that has a good fit to the KSC data is their most extreme variance simulation. And even that is still not quite extreme enough. It's still about a sigma off. Now this is 8 sigma difference from what the X-ray gas fraction data is telling us. So taking the measurements at face value, weak lensing and KSC constrain feedback to be more extreme than our simulations and than our X-ray data is telling us. It's still unclear what's the origin of this difference in the implied strength of feedback, but is it really that strange? We calibrate our hydro simulations, the AGN feedback, using X-ray gas fractions primarily. And this data is coming from the most massive objects at very low redshifts. Very different to our peak sensitivity that we get from cosmic share, which is about 10 to the 13.5 halo masses at about redshift of 0.4. KSC is giving us a totally different view of feedback. So maybe our hydro simulations are just missing some mass and redshift dependence. Another option is that we're seeing different scale extents of feedback. The X-ray do a good job of telling you the cavity of gas left in the cluster after baryon feedback has blown it outwards. But it doesn't tell you how far it extends. KSC is telling you about the outskirts. It tells you, is the gas right outside the virial radius, or is it going many megaparsecs out? So it's possible that we're missing some scale dependence in our simulations too. Now to wrap up, I think there's exciting and compelling and somewhat unsurprising evidence that we don't have a complete picture of feedback yet. I'm extremely excited that we can use weak lensing and KSC and turn the question around and use them as benchmarks for the simulation to constrain these different feedback effects. What we find is that they are inconsistent with what we expect from X-ray. They want this extreme feedback scenario. And we know that we must pin this down before we get to Rubin cosmology so that we don't totally waste all of our time doing data calibration to sub% precision. Thanks.
So Alex, in this context, it's a little bit frustrating that what we can see, the baryons, we don't seem to understand very well. And what we don't see, the dark matter, we think we understand. So could it be the other way around?
So for sure, that signature, if we say CMB, BAO, CMB lensing, they are telling us the cosmology accurately. They give a consistent picture of what our cosmology is. Let them tell us what cosmology is. Then we do have a nice signature, that predicted suppression of what weak lensing is telling us about nonlinear scales. No. And there are dozens of models that would do this. Axion dark matter, self-interacting dark matter, dark energy interacting, massive neutrinos. They all give you that signature. But the problem is we can never see that with weak lensing until we can see exactly what the baryons are doing.
But there might be other ways to see the other signatures as well. So the question is how to go to larger scales and still see those other effects.
Yes, so that would be, but it could be that these non-standard effects only, the right answer for what our standard model should be is only has signatures on nonlinear scales, and then we also wouldn't see those from BAO or from CMB lensing.
Okay, comments? Please, go ahead.
So to get this extreme suppression, do you only need to throw gas further away, or do you also need to throw away more gas?
So that's a good question. If you throw away more gas, you'll break your X-ray data. So I think that's what those Flamingo variants do. They are just checking out lots more gas and emptying your halos. What we've been exploring, which I spoke a bit about in the colloquium, is can you keep that amount of gas but just blow it way further out in a way that gives you this extreme suppression? And I think the jury's still out on that.
Any other questions? Yes?
I haven't followed these fields for quite a while, but there used to be a problem that if you had enough feedback in large clusters, it would be too much for small groups. So you mentioned X-ray, so it would be no X-ray in galaxy groups. Has it been solved?
Has it been solved that we have X-ray measurements?
Simulations end, so that you can get feedback models such that it explains both groups and clusters in terms of observed X-ray emission?
So I'm not an expert in X-ray measurements, but we have been compiling all the data that we can find from this. And what we do see is that there's certainly a data mismatch in that we are getting X-ray data in the high mass regime. I don't have that plot. In the high mass regime, and our simulations, unless you go to enormous boxes like we now have available, where the simulations are telling us about a different mass regime than what we're getting from the X-ray data. Zeta would help us push to groups, and there are some new results both out and pending on that, and they will start to bridge that gap better.
And the good news is that NASA selected an X-ray mission to study,
Yeah.
the next phase.
Fingers crossed.
Let's thank Alex again.
Oh, yeah.
I'm giving away my punchline here. Pay no attention to slides 2 and 3. We are not there yet. Good afternoon, everybody. My name is Michelle Ntampaka. I am delighted to be visiting today from Space Telescope, where I'm the Deputy Head of Data Science. And today we're going to be talking about galaxy cluster mass accretion rates with interpretable machine learning. So I'm going to start with a picture of our modern cosmological model, which describes how the early universe, which was very smooth and homogeneous, evolved over time with tiny overdensities accreting nearby matter and turning into the beautiful cosmic web of today, shown on the right-hand side of this figure. So galaxy clusters live in the massive overdense regions of the cosmic web. They contain tens or hundreds or maybe even thousands of galaxies, all gravitationally bound. We can see those in the optical and the infrared. So top left-hand corner, you're seeing a JWST image of a galaxy cluster. They also contain a hot intercluster medium that is ionized gas glowing in the X-ray, primarily through thermal bremsstrahlung. So we can detect it with space X-ray telescopes like Chandra. And that's what you're seeing in the bottom left-hand corner. And then a composite image on the right. So the galaxies and the gas are all embedded in a dark matter halo that are sort of the order of 10 to the 14, 10 to the 15 M solar. And their abundance is sensitive to the underlying cosmological model. Now, we will often make the assumption, and it's a simplifying assumption, that galaxy clusters are self-similar and that the only thing that matters is their mass. But in fact, they are also described by their mass accretion rate. So the mass accretion rate, this is just a delta log M over delta log T, describes the formation history of the cluster. It's also a function of the underlying cosmological model. So our universe dictates what kind of mass accretion histories we may see. And clusters may be relaxed with a small mass accretion rate. They could be disturbed with a large one, or they could be somewhere in the middle. And traditional options for estimating this parameter from a single cluster are severely limited. So the work I'm going to show you here today has been led by my graduate student, John Soltis. If you're interested in learning more about this project, he's actually going to be here next week. So he is looking at, can we use ML to measure mass accretion rate? And if so, where is that information? We are using multi-wavelength observations, so both X-ray and microwave, so TSZ. That X-ray information has been binned into 3 energy bands. And he's using a machine learning model that takes first a convolutional neural network. So CNNs are used for image recognition. They are really good at extracting features like textures and gradients. And At the end of that CNN, it's been adapted so it outputs a probability distribution rather than a single value, so you can get some measurement of the error bars on top of it as well. All right, on the left, analytical theory. On the right, the machine learning technique. Okay, let's talk about the analytical theory. This analytical theory is from the Benedict Deemer's 2020 paper, which explores mass accretion rates as a function of cosmology and cluster mass. And for a single cosmology, which is what we have, it's simply a function of mass. So the sharp line you're seeing at the bottom is actually just a function of our mass selection of our sample. You are hopefully thinking to yourself, why is she putting up a straw man figure? And I'm glad that you're thinking that to yourself. In fact, there really aren't a lot of options on the market. So there are no really good mass accretion rate estimators that I could put up here on the left-hand side. All right. On the right-hand side, the machine learning results. You can see there's a pretty big scatter, but it is able to capture a lot of the low mass accretion rate and a lot of the high mass accretion rate values. You'll also notice that it tilts a little bit down, sort of at the top right-hand corner. You're seeing it's kind of underestimating. That is a function of our training sample not having enough high mass accretion rate clusters to really be able to learn what that pattern looks like. But this is not the end of the story. I think as a field, we need to be thinking a lot about not just taking a data set, taking a machine learning algorithm, smashing them together, getting a factor of 2 improvement and calling it a day, but rather we need to be interpreting those results. And so John has pioneered a really interesting way of interpreting this. He takes the mock observations and divides them into a symmetric component and an asymmetric component. So in the asymmetric component, the red is an addition and the blue is a subtraction from the symmetric component. So for an example, we're going to make some Franken clusters here today. On the left, a high mass accretion rate cluster divided into its 2 components. On the right, a low mass accretion rate cluster divided into its 2 components. These 2 clusters happen to have about the same underlying mass, just really different formation histories. And to help you keep track of everything, the high mass accretion rate, I'm going to put a green star. The low mass accretion rate, I'm going to put a white hexagon just so you can track what's going on the next slide. We're then going to mix and match. All right? We're going to take a high mass accretion rate symmetric component and a low mass accretion rate asymmetric component, combine them and make this new Franken cluster that is one that the machine learning model has never seen before. And we're going to see if it works. Or actually, we're going to see what happens and try to make sense of our model from that. All right. Left-hand side, same figure that we've seen before. On the x-axis, true mass accretion rate. On the y-axis, predicted. All right, just from the regular clusters. The middle is when we make the Franken clusters for clusters that have similar masses and similar mass accretion rates. So they're kind of cousin clusters, right? And when we start to mix those things up, the results are really similar as we've seen before. So that's kind of interesting, that it doesn't seem to be a strong correlation, but rather that those 2 components both kind of get a vote. The right-hand panel, we're just handing it the symmetric component. And it's really underestimating mass accretion rate. And that's kind of a relief as well, because low mass accretion rate clusters tend to be more spherical, they're relaxed, they tend to be smoother, and so it's doing exactly what we would expect. Okay, as before, some measure of the true mass accretion rate on the x and the estimated on the y. These ones get a little more complicated. We're now making Franken clusters where the mass accretion rates vary wildly from one another, right? On the left one, the x-axis is the symmetric mass accretion rate, and the y-axis is predicted. It looks like the model cannot make a good estimate of mass accretion rate just from this. It's large errors. The middle one is the asymmetric component. Again, really large errors. And on the right axis, I'm showing the average of the 2 that we put in the Franken cluster compared to the estimate. It is not as good as the full machine learning model, but those errors have tightened just a tiny bit. All right? So there must be some really complex interplay between the symmetric component and that profile and the clumpy component that is allowing the machine learning model to make those estimates. All right, quick summary slide here. We have found that machine learning can estimate the mass accretion rate of clusters about a factor of 2 better than an analytical model, but there aren't a lot of analytical models to choose from. Our interpretation of the Franken clusters yields some really reasonable results. First of all, the smooth component is estimated as having a low mass accretion rate, which physically makes sense because it looks like a relaxed cluster. And the information in the cluster is not limited to the asymmetric component. And a final slide I'm going to put up here. If you or one of your mentees are really interested in building your machine learning expertise, I want to point you to this resource. So Hello Universe is a collection of pedagogical code and curated data that I've been leading at Space Telescope. We have built these Jupyter notebooks designed with novices in mind, designed actually with the astronomer in mind and a novice user of machine learning. We are also, if you're an expert user of machine learning, we're also accepting submissions, which we will hold on to and make publicly available until the heat death of the universe. So if this is something that you're interested in, please go ahead and grab that website. All right, and now I'm happy to take questions.
Thank you so much, Michelle.
Thanks.
These are clusters of galaxies, so in principle we have additional information on the galaxies, right? So you could look for clumpiness or subgroups within the cluster, or velocity information would definitely help. Have you looked into that?
So this is a really good question, and it's one that we're thinking about. So when a galaxy cluster is accreting matter, no, let me back up half a step. If you look at the line of sight velocities of galaxies within a cluster, they'll tend to have kind of a Gaussian distribution, and the width of that distribution scales with the mass as a power law. In the case where a cluster has recently undergone a major merger, it will tend to have a wider, flatter velocity distribution with bigger tails. And so the information actually should be in there in the dynamics as well, in the kurtosis of the velocity distribution. So I think this is actually a second signal that we could take advantage of. And right now we are not, but that is definitely something that's on our radar. Yeah.
Please.
Somewhat relatedly, it looked like the analytic method had basically 0 predictive power. So is it the case that before this machine learning method, you just wouldn't try to estimate gamma for morphology?
I mean, it does, the predictive power is really limited, and to my knowledge, there are not a lot of strong methods that can estimate mass accretion rate. Now, let me be a little careful, because a second thing we might do is divide our clusters up into categories. So rather than saying I can attach a floating point value to the mass accretion rate, I might say this is a relaxed cluster or this is a disturbed cluster. And there are, in fact, morphologically based estimators for categorizing those. We're asking a slightly more complex question, which is like, could you rank order them according to their mass accretion rate?
Yes, you and then Eric after.
So when you decompose the whole image into the smooth one and the non-smooth one, and if you only use the smooth image and retrain this part, where you shrink the scatter between the true value and the estimate value. So to demonstrate it kind of the dimensions in this kind of parameter space.
So are you asking about sort of changing the field of view? Can you ask
Changing
your
the whole image.
Changing the whole image.
Because you decompose the whole image.
Mm-hmm.
And if you just use one part of the image and treat it as a kind of real image and put it in the code machine, where you get a smaller scatter between the true value and the estimate value of the operation.
So in the case where we were just using the smooth image, that's this one over here. And so it's not actually smaller scatter, it's underestimating. Yeah.
Eric?
So this gamma is some log mass per time, is that?
Correct.
So on the left there, then the spread or the root mean square error off the linear fit is maybe 10, and then at low mass accretion rate, maybe 100, high mass accretion. So is that a good number? Would you, if you know that number to within 10, what does that tell you then? What do you learn from that?
Yeah. Can I come back in about a year and a half and answer that question? Because this is, in fact, sort of the next step, right? Now that we have some understanding of what sort of error bars are associated with a single cluster mass accretion rate measurement, the next step is exploring, like, what can we do with that as far as cosmological constraints? So, unfortunately, my answer right now is I don't know, but my calendar is totally clear in 2026. So, am I inviting myself back? Okay.
Speaking about 2026, you presented this work with a student that has natural intelligence and a machine learning model. And do you lose any sleep about, let's say, in a few years where machine learning might be better than students?
I actually would really love for a field for us to explore the question of how can, like, large language models, machine learning, help us to speed up our work in an ethical way. I think none of us wants OpenAI to be deciding the ethics of how we are using large language models to do astronomy. And yet, there's something interesting there. So no, I know John, and I'm not worried about machine learning surpassing him anytime soon. But I do wonder if a machine learning model that could have helped him find bugs in code and interpret outputs, could that have gotten this result from him a little sooner by getting him past some of the steep bits of the learning curve? And not just him, right? Me too. I still get errors that I don't understand. So I think that's a place where there's a potential. Yeah.
Let's thank Michelle again.
Okay. Hi everyone. I'm a new postdoc at ITC, and I'm happy to give this launch talk. So today I'm going to talk about some supernova stuff. So for supernova science, one of the most important tasks is to link different types of supernovae with their progenitors. So now we know type 1a is an explosion of white dwarf, and other types of supernovae are related to massive stars. And as I will show you today, the supernovae and their precursors can also give us some insights about the final stage stellar activities of those massive stars. So let's start with those type 2 supernovae. So for this type of supernovae, their progenitors are red supergiants. And recently, it has been clear that there should be some dense circumstellar materials around those red supergiant progenitors right before explosion. And one of the evidence is from the Likert modeling. Like for this type 2 supernova, we found that we have to involve some kind of CSM interaction to explain the early Likert bumps. And also, for many type 2 supernovae, there are narrow emission lines in the early spectra, which disappear just a few days after their explosion, which is also an indication that there are some dense materials out there. And for one type 2 supernova, there were even some pre-explosion activities observed up to a few months before the explosion. And also for the, yes, so this is supernova 2020 LF. And for this supernova, there were also some narrow emission lines observed in the early spectra. So a very likely scenario is that there might be some pre-explosion outbursts from the red supergiants, which produces the dense materials we infer from the light curve and the spectrum. Dense materials are also pretty common in those interaction-powered supernovae like type 1b supernovae. So here N stands for narrow, so which means there are some narrow lights in the spectra. And in this case, the narrow lights can last pretty long, so which means you know, the materials should also be pretty extended. And for some cases, for some type 1b supernovae, pre-explosion outbursts were also observed, like 1 or 2 years before explosion, which could be linked to the dense materials around their progenitors. So for today's talk, I will talk about 2 things. So the first is the precursors, or the precursor search for a type 1b supernova 2023 FYQ. And then I will talk about this precursor search for those normal type 2 supernovae. Okay, so for type 1b supernova 23 FYQ, we identified a very long-standing precursor activity. So here, this vertical dashed line is where we think the explosion happened. And everything before that is pre-explosion activity. So if you look at this, this plot, so here this blue line is the temperature evolution. And as you can see, before this dashed line, the temperature is pretty stable, which is around 10,000 K. And around here, you see a big jump in temperature, which is due to the shock breakout from the explosion. So this supports that the explosion should happen around here. And when we searched for more archival images, we found that the precursor can be traced back to around 3 years before the supernova explosion. And if you look at this volumetric light curve, you can see the precursor light curve has a pretty smooth rise right before the explosion. Yeah. And from the post-explosion light curve modeling, we found that so right after the initial shock breakout, the main light curve peak is dominated by CSM interaction, and which means there are a lot of materials, you know, around the progenitor. And also from the spectrum taken around 20 days after explosion, we found that the object is pretty similar to a type 1c supernova. So the progenitor is likely to be a stripped star. So by putting all this together, here's a scenario we propose for this supernova. So we think there should be a binary system there which has a helium star and also a compact object which accretes materials from the helium star. And we think the accretion powers the precursor emission. Also the outflow during this process, produces the dense materials around the progenitor. And as the orbit shrinks, the accretion rate will increase. And in that case, it will explain the rise we see in the precursor light curve. And this scenario is also supported by those theoretical studies. So here these dashed and solid lines are theoretical models made by Daichi Tsuna based on this scenario. And as you can see, these model light curves are pretty consistent with our observations. Okay, so then let's talk about the precursor search we did for those normal type 2 supernovae. So as you may know, this year and last year, there were 2 very nearby type 2 supernovae exploded. So one is 2023 XF, and another is 2024 GGI. They're all exploding at around 7 megaparsec. So this provides a very good opportunity for us to search for any possible precursor activities. And also for these two type 2 supernovae, there were also narrow lights observed in the early spectra, so which means there should be some dense materials around their red silver-giant progenitors. So we searched for the archival images for some public surveys, and here are what we got. So all these small dots with arrows are all non-detection limits. So which means basically we don't see any precursor activities up to around 7 years before the supernova explosion, for both of these two supernovae. And the limits we can put is if there were any precursor, it should be fainter than around -9 and -8 and -9 magnitude. So this is actually pretty interesting. So if there were no precursors, then where do those dense materials come from? And there are some possibilities. So, for example, maybe there was some precursor out there, but there was also some dust around the progenitor. And in that case, it would be hard to detect the precursors in optical. And another possibility might be the dense materials around those stars are actually the chromospheres of red supergiants. And some recent studies have shown that with this chromosphere like CSM, all those observed features like the narrow emission lights and early light curve bumps can be reproduced. And in this scenario, we would not expect to see any precursors because there were no outbursts from red supergiants in this case. Okay, and here's a summary. So, yeah, so supernovae and their precursors can really help us to constrain the final stage stellar activities of massive stars. And we're also seeing some type 1b supernovae, maybe from maybe exploded from Banner system, which has a helium star and a compact object companion. And also, we found no precursors in two very nearby type 2 supernovae, which means there might be some dust around the progenitor, or the dense materials may come from the chromosphere of red supergiants. Yeah, that's all. Thank you.
One can tell the difference between dust and a chromosphere scenario because the dust would affect the light curve at different wavelengths differently, right? So
yeah.
And the chromospheric scenario would apply to a lot of objects because there is always something around.
Yeah, that's true.
So I guess you just need more objects of this type, right?
Yeah, that's true. So one thing interesting is, like for these two nearby supernovae, we don't see precursors, but for another type 2 supernova, we do. There were indeed some precursor detections. So there might be, some different physical mechanisms behind the dense materials around progenitors. Yes.
So when I think of a chromosphere, it's a very narrow layer on top of the star, like the sun's chromosphere.
Yes.
You want a lot of CSM spread over a range of radius, I think.
Okay, so in this case, we actually don't need a very extended material since, as you can see, for those narrow features, it only lasts for like a few days. So, yeah, so the CSM should be pretty confined, should be very close to the.
A few days is still a long way, right?
No.
At 10,000 kilometers per second.
No,
No,
it's just twice the radius.
Twice the radius, yeah. Still a fairly thick layer. So is your chromosphere doubling the radius of the star? I mean, how thick is this chromosphere?
Well, yeah, I'm not sure about that,
2R star, 3R star. I'm just confused because I think of the solar chromosphere. It's not going up to 2 times the radius of the sun.
Right. Yeah. Okay. But I think even if it tends to. Okay. Let me see. Okay. But anyway, so to produce this observed thing, I think we only need some CSM which is dense and confined. Yeah, but from theories, I think they can produce this observed effect. Yeah.
Any other comments? Since we were discussing transients, I just wanted to say how proud we are and that Ashley Villar received the Packard Award, and we are all delighted with the news that came out just a few days ago. So congratulations. And let's thank Yize again.
Good afternoon. So my name is Rodrigo Córdova Rosado, as Avi mentioned earlier. I'm a final year PhD student at Princeton. I was an undergrad here, and I distinctly remember being very frightened when I gave my senior thesis talk right in this room, I think right from this podium. So this is a nice, deja vu moment. But today I'm really excited to talk to you all about this exciting work that we've been doing, myself, Jenny Green, Andy Golding, and other collaborators in HSC down at Princeton, thinking about the connections between the parsec scale phenomena that AGN and our spectroscopy of AGN probe with large-scale clustering. So a little of the context, as Alex just talked about a minute ago, we're really curious to try to understand feedback processes and how AGN these parsec scale phenomenon that are giving these orientation effects and how AGN more broadly are having this interaction with their host galaxy and what the different kinds of host galaxies that we observe, how they're whether or not that is in fact telling us something interesting about different AGN evolutionary models, if AGN are just one large population and we're seeing different parts of the spectrum of variability, or are there in fact different things that we can probe using large-scale structure tools, since of course direct observations of AGN are difficult because they're so compact and so luminous that you can't resolve the host galaxy nearly as well. And particularly one of these leading questions for the last number of decades now has been this question of type 1 versus type 2 AGN. Type 1 being the unobscured AGN, type 2 being obscured. And here what this diagnostic plot is trying to show is what the characteristic differences, one being this unobscured AGN population, the type 1s, have a strong UV power law light continuum, strong broad emission features in all the permitted lines. You can also have these slightly obscured or red quasars where you still have evidence of broad lines, but you see significant obscuration, or kind of the classic type 2 or obscured narrow line AGN. So there's all these kind of layers of selection and decision making on how you make these samples, be they spectroscopic, photometric, that we'll get into a little bit today. And in particular, as I mentioned, there's this idea of a unified AGN model, where depending on where your sight line is relative to the orientation of the accretion disk and the torus that surrounds the accretion disk, you might have different ideas of whether, well, if it's a narrow line AGN, if it's a type 2, it's because you're seeing them edge on, and you're seeing the dust from the torus blocking the broad line emission from the broad line region closer to the accretion disk, whereas unobscured AGN, you're staying straight down into the accretion region and not having these torus effects that might block it. But as others have noted for more than a decade now, is this actually just reflective of some kind of evolutionary sequence, some kind of more interesting story? And for example, you can read something like Phil Hockman's theory from 2008, or Ryan Hickox's paper from 2009 and 2011 that describe these ideas of whether you have these hierarchical merging scenarios that you go from type 2 AGN, for example, that are more likely to be found in merging states, that then you have these blowouts that people like Victoria Fawcett and Desi has been talking about and thinking about what the radio emission from these very dusty broadline quasars might be, and do you kind of relax into a type 1 quasar? Is this kind of picture appropriate? And also, as we're learning more and more about high redshift AGN in the universe, how do those early seeds, how do they kind of fit into this global picture of AGN evolution? And clustering is this really unique technique because it lets you sort through the rest of the story to get at the halo masses, get at the host halo masses for the different kinds of AGN depending on your selection. And as these plots are trying to show, the results are all over the place. You have some finding that obscured AGN are more massive. Some are finding that unobscured AGN are more massive. Many are finding that there's no statistically significant difference. And what we thought we could do is that we can peer and to understand which physical picture, which model is more accurate based on the deep observations that we have in the optical from High-Breadth Prime Cam, and in combining them with mid-infrared observations from the Yize telescope, we can make a more robust sample of AGN that, compared to previously, we only had about of order 100, 150 per square degree optical plus mid-infrared selected AGN across wide swaths of the sky. That's STSS. That's the Yize AGN catalog. And what we found is that we can create a much denser catalog. So what exactly are we doing here? As you can see from this kind of example of a classic kind of type 2 quasar versus a elliptical galaxy, where on the background you can see the filters for HSC in the optical on the left and the mid-infrared filters from Yize on the right. It is critically that information from the mid-infrared that's getting you the information that there is strong mid-infrared emission coming from AGN. That's the prototypical picture that we have. And using that information as well as compactness criteria, we can sort through not just whether it's an AGN, a galaxy, or a star, but also what kind of AGN is it? Can we actually divide these samples appropriately just from the photometry? And in particular, what Andy Golding, this is Andy's work that he's been leading, is thinking about how you use unsupervised machine learning techniques to just sort through all this photometric data and then compress it back down to 2 dimensions, and finding that these, when you pass all the kind of prototypical STSS type 1, type 2 quasars through this now trained system, they all land in these 2 clouds. So we're saying this is potentially doing a very good job of separating the AGN from the rest of the galaxies and the rest of the sources in HSC, and we can then drill into this particular population and understand, for example, the unobscured, reddened, and obscured categories of AGN, and whether or not, as I'll show in a minute, they cluster at different rates or not. So what did we do? Ultimately, we do a k-nearest neighbors algorithm in order to find the minima between these different distributions, and kind of like from the photometry alone, describe them as, again, unobscured, reddened, or obscured. And then we take a cross-correlation, considering that this is a sparse sample of AGN. We want to get as many points to cross-correlate with, so we take the luminous red galaxy sample from HSC as well, and we have over 1 million LRGs and more than 28,000 AGN in our redshift and luminosity range. So that's the other critical piece, understanding the luminosity distribution of your AGN and knowing the redshift distribution of your AGN. For this sample, we have a redshift for every single source. The vast majority of them are going to be photo-Zs. They have uncertainties. That's the other thing that we needed to take care of. So many folks will be familiar with this equation. This is just a prototypical projected angular correlation function, where you're just measuring the number of data-data pairs as a function of an angle relative to the number of random pairs from a completely random distribution that you compare with. And based on this, the excess data pairs, that's how you're going to measure a clustering statistic. And what we added onto this was a weighted statistic to make sure that we're folding in the uncertainties that we have from our photometric redshifts. So now you're not just worrying about, as often in tomographic style analyses of redshift bins, of whether or not an object is falling out of your redshift bin, how much of it is falling out of your redshift bin. You're also worrying about objects that are falling into your redshift bin. So doing this in as much of a self-consistent way as we possibly could, splitting the different samples, measuring the angular correlation functions, we find that there's already a 5 sigma difference in the amplitude between the unobscured and the obscured AGN. And then once you fold in your physical model of linear dark matter and measure the clustering strength relative to that dark matter model, which is dependent on redshifts, luminosities, all these, well, redshift specifically, you get the following result, where the unobscured AGN, at least at face value, seem to be living in dark matter halos that are 5 times larger than the dark matter halos in which obscured AGN live. And when you mix up the different combinations of obscured plus reddened plus obscured, you see this nice kind of like linear model appear of what is the direction in which these AGN are preferentially living in different size halos. And we find that so I'll be clear, the parenthetical sigmas on here are when you fold in the 5 sigma and 3 sigma results, not in parentheses, are when you use just the diagonal of a covariance matrix to do these estimates, which is very common in this particular field using angular correlation functions. But we wanted to also fold in and present what happens when you use the full covariance matrix and the off diagonals, and those are the parenthetical significances. But we also noted, as we found in this analysis, that small systematic uncertainties in your redshift distribution, case in point that red arrow, if you shift your redshift distribution by just a tiny amount, that's enough to completely wipe out your signal potentially. So instead, what we did is we wanted to think what was next. How can we improve this measurement, and how can we kind of resolve these systematic uncertainties? And for that, we turned to DESI. So using the public data, the early data release from DESI, we found that we could find more than 5,000 matches between our HSC sample and the DESI early data release. And just to flash this picture again, from the spectrum, we have this idea of these kind of like 3 broad classes of AGN that we're probing. We find them in DESI easily. So it's really fun. It was really fun, and well, it was a couple of months of me staring at several thousand of these AGN, sorting them all out, and making sure that our automated spectral fits and classifiers were doing a good job of what you could kind of piece out by eye. And specifically, what you can find here, right, of course, is the unobscured AGN with these strong UV continua, big, broad absorption emission features. Then you have these obscured reddened AGN, where you still have broad line features, but you have significant obscuration. And then classic narrow line AGN, where you still know, for example, the key neon 5 emission. That's a high ionization line that is kind of a smoking gun, as it were, for AGN activity, as well as the line ratios between the permitted lines and the forbidden lines, like O3 to H beta. Those are all kind of key things that let you understand something about the AGN. When you then compare what our final spectroscopic classification was relative to our photometric classification, you're finding A, that 76% of the sample are spectroscopically confirmed as AGN, where what I'm showing here on the right is the probability based on the photometry that they are a type 1 based on the HSC and Yize photometry versus the final categories from spectra. And you're finding that for the type 1s, it's following very precisely, and for the different objects, it's going a little bit different. So let me just speed up to the last point. So from HSC plus Yize, we're now getting that this is a 240 per square degree sample. That's close to double what previous AGN catalogs would show you. And many of these are broadline AGN, which is to be expected, considering that DESI specifically targets for broadline AGN. And when you finally do the clustering, you do the 2-point correlation analysis, you get the same amplitudes. So smaller significances, the overlap at the end of the day was only about 50 square degrees, not 600 square degrees we had in DESI. It's going to get better once we have the full DESI year 1 data. But you're already seeing that the amplitudes match quite nicely for the different kinds of AGN. And so the next steps that we're going to be thinking about is how we're going to cross-correlate these signals with CMB lensing maps, get independent halo mass constraints from those, think about extensions with the DESI datasets, think of a lot of other interesting things that we can do there, thinking about dual AGN, outflows, a lot of the questions that come back to feedback. And also we want to be able to leverage the intra-halo clustering that so far we've had to throw out because we don't have sufficient modeling capacity to think about what the intra-halo, satellite fractions, central fractions, all those kinds of things about AGN, what that tells us about the clustering dynamics of these objects. And ultimately, the Rear Rubin Observatory will give us access to millions of AGN over half the sky. And in combination with DESI, we're going to explore AGN properties found in clusters and think about all these kinds of interesting feedback questions that Alex laid out. So with that, I'll leave up my summary slide, and thank you very much.
Perfect timing for the end of your PhD with the LSST data. But the transition in halo mass that you are referring to is actually the transition between gas-rich star-forming galaxies and elliptical galaxies in a way, right?
Potentially. I think that's the question of what exactly is this halo mass transition that is probing. And I think we have one potential model. Is this just like hierarchical story where you're doing that switch from spirals to ellipticals? But at the same time, I think there's enough variability out there in the universe that we've already seen from other AGN surveys that we really need to just keep thinking about selection functions, luminosity thresholds, and a lot of other parameter space that needs to keep being explored.
There was a question here.
Yeah, very fantastic. So can you say 76% of your AGNs are spectroscopically confirmed? Which of the emission lines or absorption lines you're characterizing as an AGN evidence?
Sure. I mean, the key thing is there's 3 steps fundamentally. Is there a broad line feature in primarily the ones that we're most sensitive to, magnesium 2 and H beta from this redshift range? That's the first step. If there's a broad line feature, we're taking that as unambiguous evidence that it's an AGN. At the end of the day, this is also a confirmation. There's already a layer of HSC plus Y's characterization and selection, and this is just further evidence that we think that these are in fact AGN. We have the mid-infrared information as well that already led us to think of these as potential AGN. So first step is the broadline feature, second step is a significant neon 5 emission line, and third is whether or not it passes these kind of Baldwin Phillips and Turlovich style relationships between strong line diagnostics. So particularly what we used for this paper was the O-no diagram, the O3 to H beta and neon 3 to O2 line diagnostic. Those were the key things that made the sample selection for the AGN.
Last question?
Very quickly, yeah.
Yeah.
Bottom line.
Yeah.
See, there's a standard picture that type 1, you're looking face on, type 2, you're looking edge on and getting obscured. You're saying that the two are different, they have different halos. So are you ruling out the simple geometrical picture, or are you saying it's just a little more complicated but still basically okay?
I think the fundamental, let's say it this way, the most simple unified model, I had a long conversation with Meg Urey about this the other day. The most simple unified model for this luminosity range, for this redshift range, is not describing the data. That could be an effect of our selection choices. There could be other things going on there. We think we're trying to do the best possible job we can. And at the moment, for this range, luminosity range, it might not be sufficient to explain the data that we have.
Be very careful. So you're not saying it's
Well, it's good that the young correct the mistakes of the old. So I feel comfortable about doing that. So let's thank Rodrigo again.
Yeah.